Guys, I'm back again. So the last time I recorded was probably around week 2, but it turns out the students found the questions from Rice. So this was for 43 and 44 in chapter 9, the most difficult. So this is the likelihood ratio and the goodness of fit. So this is actually looking at the chi-squared test statistics, right? So usually this chi-squared, is constructed when you are squaring things that are actually normal. So we are, we're going to be looking at the goodness of fit, which happens, or the goodness of fit test, which happens to be something that's distributed, chi. And we're going to use a chi-square distribution to really determine whether or not like we have significant differences and things that look discrete, right? So, the reason we're using goodness of fit here is because we're looking at things that are discrete. And of course, we cannot use any of the stuff we used before, the t-distribution and whatnot, to assess discrete outcomes. So this is why we've introduced this notion of goodness of fit. So let's start. So at some point, because question 44 and 43 are so dichotomous, well, they're related to the same chi-square test, but they both are rather involved. I'm going to actually pause at some point and say, I'm going to change questions. So you might see a lag or a lull at some point where I'm kind of trying to switch gears. I apologize for that in advance. Okay, so this is actually, the first question is about, so in 1965, it turns out a newspaper carried a local story about a high school student that reported getting 9,207 heads and 8,743 tails and something under 18,000 coin tosses. The question is this a significant discrepancy from the null hypothesis that p is equal to 1/2? Well, the first thing you'll notice is that this is a Bernoulli process, right? So usually when you have something that's Bernoulli, you cannot use a test statistic t, because t-distribution on some implicit level is assuming that at the population level, things are normal. But when you have an outcome that is discrete, that just can't really be feasible, right? So this means that we're in some sense going to demand, right, that our sample size is large enough to even construct this Z score. This is notion of the central limit theorem says that if I take many samples that is this large, in this case, almost 18,000, I'm going to construct multiple p hats. And the question is, how far off are these p hats to construct for every different realization of these samples from 1/2, basically, right? So this, and obviously you're going to construct a distribution on this. And the theory is that if you sample large enough, the distribution you create across these different sample p hats will look normal. Right, so this is the idea that gives us this construction of a Z statistic to answer this question. Right, now the other thing you might notice is that this is a pretty large sample, right? So you might intuitively think, well, doesn't that mean that, right, 0.51 isn't that much different from 0.5, right? But when you have really large sample sizes, it turns out that you can actually observe minute differences more saliently, right? So even though 0.5 only differs from 0.13 by 1.3 to the right, in the case of the p hat, it turns out that you can uncover very small differences between your sample estimate and what you hypothesize when you have really large sample sizes, right? So you'd be surprised at the finding here that you may not reject the null hypothesis, even though it seems like your estimate, which is the number of heads, in this case 9,207, it shouldn't be that far from 17,950. Right, sorry. So it seems like, this estimate of 9,207 divided by 17,950, which yields 0.51, shouldn't be that different from 0.5, but actually you may actually see you reject a null hypothesis. So I'm going to construct a Z score on the, the Z score that's based on the score. So this means I'm going to use the standard error for P naught, right? So there's a walled statistic that allows you to use the standard error based on P hat. Right, so but I'm going to use P naught, and you're going to see it's just for more robust, right? So because it's more robust, I'm going to use it, but I'm going to do a double check to ensure that I can even be certain that my sampling distribution along the null is going to be normal, right? So this gets into the idea of like how large is the sample to be sure of a central limit theorem. But this is very large, right? So you only demand, the central limit theorem says that if your sample size is bigger than 30, you have some confidence basically that maybe your sampling distribution is normal, but this is a lot bigger than 30. So, right, in fact, you ask that n times p and n times 1 minus p should each be 15. So when you add them, you get 30. but each of them are going to be like something under 9,000. So they're both very big. So we can construct this test statistic. Okay, so I'm going to construct it, and you can see that, like I said here, I'm going to construct this z-score around p naught, right? So this is where I said I'm going to use a standard error of p naught rather than that of p hat. So this is the score. This is a z-score based on the score. There's something called a Wald test statistic. I'm using the score test statistic, but Wald's have replaced p hat instead of p naught. Actually, they should both yield the same idea here because the sample size is so large. But when your sample size is small, you may not want to use p hat because it's can be unstable in small samples. But it's actually pretty large here because you have almost 18,000 observations. So they should yield. It should be pretty stable. But just for the consistency, I tend to use p naught. Anyways, when you plug this in, you get the estimate you saw in the sample was 0.153. We hypothesized 0.5. And like I said, this doesn't seem like a huge difference, right? So if you look at it, it's like 0.13. But because this n is so big, you can imagine that this thing here is really small, right? This is a really small number. And so you're taking this really small difference and you're in fact dividing it into something that's huge, or sorry, something that's really small, right? So this is a very small number. So even if this is a small difference, because this is a lot larger than what you're going to see here, it will blow up the test statistic. So it ends up being 3.4. So on the z-score scale, this is actually a pretty extreme outcome because you can imagine that the z-score, the z-table, a standard normal, doesn't really have long tails, right? So it doesn't really go beyond -3 and 3 too much, right? So even though it seems as if this difference of 0.15 minus 0.5 should be somewhat small, in fact, it's pretty large, right, on the Z table, because again, the Z table doesn't have long tail, so 3.5 is pretty far out there, right? And so I'm going to use the p-norm function. So you guys have a table, but I'm so used to using R, I just kind of use the p-norm function. So the p-norm function is a quantile function. It gives you, if you give a quantile, so 3.483 is the quantile, right? It's the z-score, and I'm gonna ask for given quantile, please give me the p-value for it. So this will give me the area behind said quantile, right? So if I draw a little thing in the corner, hopefully it lets me. And you can see that it's going to give you the area behind your z-score. So if this is like 3.483, it's going to give me the area behind it. So what I really wanted, I don't want the area behind it. I want the area above it. You might say, why do you want the area above it? The reason why you want the area above it is because you're interested in, right, obtaining the extreme values, right? So you want the extreme values here. And so therefore, of course, you're going to ask, right, for all the observations ahead of it. So what you really actually want is the blue region over here, all the observations as extreme or more extreme than that. So I'm going to actually do 1 minus the CDF. So this gives you this is a CDF of some sort, the p-norm. So I'm going to do 1 minus that to get the area ahead, right? So if I go to R and I put something like, 1 minus p-norm of 3.483, I'm going to get 0.002, etc. But I need to multiply this by 2 because this test is two-sided. I didn't specify a side. This is a two-sided test. Right? And so therefore, I'm going to multiply it by 2. So this answer you have, in fact, I should have done 2 times, right? 1 minus p-norm, 3.843. And so you got, oh, that's not right. Sorry, guys. I was like, why is this so much bigger than, this is more than twice what I saw. So yeah, 3.483. There you go. Yeah, so 0.0095, right? So what I have here is this, I have a rounding thing, right? So I kind of put in 3.87. So this is the rounding. So this is what you got here basically, right? So of course, this is really actually small, right? Because remember, we're comparing this, right, to the following. So this is obviously less than, in this context here, 0.05, which is our alpha. So if we don't specify an alpha, we know the default is 0.05. So this will result in a reject the null hypothesis, right? So in this case here, you're going to reject the null hypothesis, right? I'm going to put here, reject HO. We're going to conclude the alternative. So there appears to be a significant difference with what the student actually observed in their actual coin toss, which is 0.51, and what we actually hypothesized. And this is, of course, because even if it seems like not a big difference, when you have that many observations, in fact, it kind of is a big difference because you're consistently far enough from 0.5 that it's significant. Okay, so I'm going to pause and move to the next part of the question, which is, this is where the chi-square test comes in. Okay, so part B says, Jack Uden, a statistician at the National Bureau of Standards, contacted the student and asked him how exactly he performed the experiment. So this is 1974. The same time, the student had tossed groups of 5 coins at a time. So this means that the student was like, yeah, I'm not going to actually bother to toss one coin a number of times. I'm going to toss essentially 5 coins. Each of those have their own frequency as to how many times the coin was tossed. And then that younger brother record the results. So this, what you see here is a table of heads. So this means that how many times in the coin toss for each of those 5 coins did you actually observe like 0 heads or 1 or 2, 3, 4, and 5. So this is, they toss 5 coins, and then this is the frequency you see among the coins for the number of heads. So the question is the data, right, consistent with the hypothesis that all the coins were fair? So of course, if it's a fair toss, you expect to see p is equal to 1/2. So we can obviously think to ourselves, we cannot use the z-score here because we are dealing with more than 2 outcomes. In fact, we have 6 possible outcomes, so we need to be a bit creative here. So this is when you would use chi, because this is still a discrete process, but now we actually have more than 2 categories. So we're going to use a chi, recognizing, right, that we can look at what we expected to see under p is equal to 1/2, what we actually observed, right, under the frequency table. So if we go back to what I've done here, right, what we have here is the following. So first of all, I just want to point out that the chi distribution, unlike the z-score, so if you can see in the previous result here, when we were looking at the z-score and we said, oh, reject HO, as in like conclude the alternative, that there appears a significant difference on the z distribution along the null. But now we're looking at a chi, and the chi we know is right skewed, right? So it has a long right tail, but we did not specify a side in this context. So we are still looking at the situation where we're dealing with, a 2-sided test. But the 2-sided, we should not assume symmetry now because the chi distribution is not symmetric about, right, the mean or even the median. Okay, so now the idea here is that under HO, we have an expected amount of, under HO p is equal to 1/2, we have an expected outcome for our frequency, and what we actually observe may not necessarily match up with what we expected to see, basically. Right, so from the table, I just kind of wrote down what we observed, and you can see here that these numbers are not coming out of nowhere. They're from the actual distribution of outcomes that we saw here. And now the question is like, is what I expected to see, what I'm going to fill in here, equivalent to what we actually observed. Now, to do that, I'm going to use the fact that I know it's the binomial outcome. As in either you got heads, you got tails, basically, right? So this is a binomial thing because we have multiple trials, right? But we have multiple possible outcomes. So there are 5, of course, the number of heads you can get can be 5, 4, 3, 2, or 1, or 0. And obviously you either got heads, you got tails. This is a sum of Bernoulli's, right? Each time you do the trial, you have a sum of Bernoulli's, so you have a binomial outcome. Okay, so now we know that there's only, you can get up to at most 5 heads. So you should put, well, n is the number of trials is this, so the number of trials is this. When I say n, I'm really referring to big N, and what I mean is n is the number of heads, basically. Right, so it may not be the case that you get every time, you may not get a head all the time, but the question is, out of all the possible trials, how many times did we actually yield, right, heads? So let's suppose we actually have, for instance, like let's say 0 heads, and what you actually have is 5 choose 0. right? So, you know, times, well, obviously it's going to be 1/2 to the 5. It's because, you know, when you talk about like n choose, so if you have, you know, p to the n minus x, you know, what, you know, or p to the x, 1 minus p to the n minus x, which ends up being like 1/5 to the power of n. What actually is going to change is a combinatoric expression here, right? So, well, you're going to have 1/5 to the power of n because 1/5 is symmetric. When you subtract 1 from that, you get 1/2, right? Right. So 1/2 is symmetric. So when you subtract, you write 1 minus 1/2, you get 1/2 again. So it's 1/2 to the power of 5. But what should change is the combinatoric part here, basically, you know, the factorial. So you're going to get, and this is going to be for, let's say, p to the power of like, let's say p0, it's going to be this, right? Oops. It's always a case that OneNote gives me issues. Okay. What you're going to end up with is something that looks like 0.031, right? Because this combinatorics here ends up being, well, of course, you know, it's going to be n factorial, you know, k factorial. I should put x here, basically being very picky. Let's not mess up notation. So it should be x, you know, n minus x factorial. So in this context here, it's going to be equal to, well, you know, 5 factorial divided by, you know, 0 factorial, 5 minus 0 factorial. And of course, you guys know that it just ends up being 5 divided by 5, right? So it ends up being 5 factorial divided by 5 factorial. So what you're actually going to get is just 1, right? So now when you have 5, choose, let's say 1/2 to the 5, because again, 1/2 around, you know, 1 minus 1/2, 1/2 ends up being symmetric. So this is going to be, well, now you have 5, choose 1, and this is going to actually end up being 5 times 1/2 to the power of 5, and that's going to give us 0.156. And then I'm going to have something like, you know, 5, choose 2, 1/2 to the power of 5. So it's going to be P2. And let me kind of put this in red so you can kind of see where all the probabilities we're working towards are. So this is going to end up being, well, 5 choose 2 is going to yield 10. Right, so we have 10 times 1/2 to the 5. And you can see where I'm going with this. I'm going to actually end up, so I'm going to kind of put this here, but let me continue down here. I'm going to end up with a situation where I'm going to create, in some sense, an expected count by multiplying my total outcomes, which is, you know, 3,590 by each of the probabilities, because that should be, if you multiply the probability by the total outcomes, by the total number of trials, that should be your expected frequency. Now, if you got a frequency that doesn't make sense what you actually saw with your probability, that's when you might get rejected null hypothesis, right? So I'll repeat it again. If you obtain a frequency, right, using these in your actual data that does not come close to what you actually used here by the probabilities we computed, then that's when you might get suspicious, basically. All right, so when you put an n, you know, here, and I should put big N so I don't confuse people. I realize it, like I forgot to do that in the previous one, I apologize. But when I say n, I mean like n equals 0, or sorry, n is equal to 5 here, right? So it's just the number of possible heads you can achieve. It's not like the 3,590 possible like trials, because you only have 5 possible permutations of like five possible, you can only get at most 5 heads in your coin toss when you toss 5 coins. Right? So that's what I'm really referring to, right? So I can only toss at most 5 coins at a time. So I can only really at most get 5 possible heads. It's just that the number of trials that I actually did this on was like over 3,000. So just to clarify, the reason why it's 5 is and not 3,590 is because I'm looking at the total possible number of heads I can get when you flip 5 coins, which is at, you know, at most 5. Okay, so when you have 5 choose 3, so it's going to be equal to, 5 choose 3, 1/2 to the 5, and it's going to be equal to, ironically, you get the same thing. Wow, you get the same, you get something like 0.313, right? So, and I wonder if that's the same as the previous one. I don't think it is. No, it's not. Maybe I didn't actually put what this answer is. So yeah, it is. The reason why I said ironically it's the same is because it's the same as what you get when you put in this, and that's because the combinatoric argument you get is the same, basically, right? And it's also the case that when you look at, like, for instance, and choose 4, right? 1/2 to the power 5. You get something like 0.156, which should actually match up what you get when you put n choose 5. It matches up what you get when you put n choose, I think, 2. Right, so they end up being the same. Okay, so n choose 4 is the following. You end up getting 5 times 1/2 to the power 5, and this ends up being, I think we computed this before, 0.156, and then when you take n choose 5, you end up getting, of course, 5 choose 5 ends up being, it's actually symmetrically the same thing as what you get when you take 5 choose 0. So we know it's 0.0313, right? So because you end up getting, so just to reiterate, it's the same, symmetrically, it's the same thing as saying, like, 5 choose 5. So let me so it should be this 1/2 to the power of 5, but you guys know when you put this in the factorial, what you end up yielding, right? And I should put this as, you end up getting something like, 1, because it's 5 factorial of 5 factorial, and you get 1/2 to the 5. So you guys know it's going to be 0.0313. So it turns out the frequency, the expected frequency for 5 and 0 should be the same, right? Because it makes sense. You can imagine the probability of getting all tails should be the same as getting all heads, and that should be relatively low, right? So I believe the highest frequency should honestly load in the middle, basically, which is around, like, let's say, 2 and 3. That's where it should load the highest, right? And so I believe that 3 should have the same frequency as 2, which it does. But like getting 1 head should have the same frequency as 4 heads, because those are getting to the extreme outcome. So in the middle, between 2 and 3 should be the highest, right? Which is what you see. So that means that when we actually compute our expected counts, right? And I wonder if I did this. So I want to kind of say, let me just erase, that's the chi-square test statistics, but I want to first show you guys at least an example of how it would actually compute the frequency. So to compute the frequency, right, let me kind of just say, so example, expected frequency for, let's say, 0 heads. Should be something like 0.0313 times, well, again, I said the samples, the total number of the trials was 3,590. So it should be this times 3,590. What we actually obtain here is something like 112.5. It should be 1112.5. And if you can imagine, this ends up being, which is equal to the expected frequency for 5 heads, because they should be the lowest outcome, because it's pretty unlikely to get all tails or all heads. right? And then if you keep doing this, I'm going to leave the guys for you guys, but if you keep playing this game where you multiply all the expected probabilities, you'll see that the expected counts for 5 heads, sorry, for 4 heads and 1 head should be the same. And then in the middle with 2 and 3, you should have the same expected counts. So what I end up getting basically is the following. When I fill it in, I get 112.5 for this and 112.5 for this. And similarly, I get 560.9 for this, and it should be the same as this one because they're also relatively rare. And the highest, oh, this should be 9. The highest outcome should load in the middle, basically, right? You should see the biggest frequencies in the middle, which would you expect to see at least. So this is 112, 1.9, 1121. Make this better. So you can see that the highest frequency is expected in the outcomes is 2 and 3, because if it's a fair outcome, you should expect to see somewhat of a balance between the number of heads and tails you get. So when you get 2 heads, you got 3 tails, or you got 3 heads and you got 2 tails, which is something close to a half. But when you get to the outer portions, is getting to the extreme observations, which is kind of unlikely, right? So now let's think about this, because what we're actually saying here, right, is that the chi-square test statistic is going to be the difference, literally, right? So it's going to be the sum across all the possible number of heads. So in this case, it's going to be 5. What you observe minus what you expected, and you're going to have to standardize this. You standardize it by expected counts. And if you literally sum up all those things, so this means the first one should be equal to, you know, what you observed is 100. What you expected is 112.5 squared divided by 100. And we're going to keep doing this plus all the way to get to the last outcome, which is the same basically. I'm just going to say dot, 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 and I'm going to tell you what the outcome is just to save like time and space. So you're going to get, you know, 1, 1, 0. So this is the 5th outcome. So these are the tail ends basically. And you got all tails are all heads. And if you sum them all up, you should get something like 21.25. So 0.58, which is pretty big. And this is because if you look at the actual table, you'll see that the expected counts are rather low here. Like what you should have seen, if it was a fair toss, you should have seen more here. You also see pretty high outcomes over here and pretty low ones over here. So you're getting a bit confused, which indicates that it might be a slightly imbalanced or a slightly unfair coin toss. So it's slightly unfair because what you actually got is in some instances either overshooting of what you expected to see or an undershooting. So it's a slightly imbalanced coin toss, you can kind of see, but the question is how imbalanced, right? Is it really that extreme? We need to conceptualize this by looking at the chi-square test. So this is when we actually look at the quantile function again for the chi, right? And so I'm going to use R, obviously, because that's what I do. Right, so I'm going to use Q chi squared. So I'm going to use Q chi square, and I'm going to use 0.975 because it's a two-sided test. And then I'm going to use, well, 5. Why 5? Because the degrees of freedom is going to be equal to n minus 1. It's going to be equal to 5 because n is actually, so in this instance here, or let's say k minus 1. Let's use k minus 1. So k is the number of groups. In this instance here, there are 6 possible groups because you can get 0 to 5. And so its degrees of freedom is going to be equal to 5. And so if I put this into the actual chi-square table, so let's use this here. So I'm going to use a 0.975 for two-sided test. And then I'm going to use, let's say, my degrees of freedom of 5. So what you get is 12.8325, right? This is going to be equal to 12.8325. So what am I actually saying? What I'm saying is that my actual critical value is here, 12.83, let me double check, 25. And my actual true statistic is somewhere out here. So what I actually observed is somewhere here. So obviously in this context here, I'm going to reject the null hypothesis. So this is a reject HO, right? So we reject HO. So let's color code this. So reject HO. This is the critical values. This is critical value. And it appears that our critical value is actually less than what we actually observed, which is 21.58. So this is we're going to reject HO here. We're going to conclude that we appear to have a significant difference between what we expected, what we saw in our observed counts, and what we expected under the assumption that, right, that we're looking at a fair coin toss. Okay. Now, the question has a little twist here because you can see that, so the question is going to change here because it says, is the data consistent with the hypothesis that all 5 coins have the same probability of heads? But this was not necessarily 1/2. So you might say, how did the question change? How is B different from C? Isn't it asking the same thing? Because they're saying in part B, is the data consistent with the fair coin toss if P is equal to 1/2? But it's not quite the same because part C is saying, is it possible that you do have the same coin being tossed in 5 different trials, but it's not a fair coin toss? So it's asking you to use your hypothesized P from part A, right? So remember in part A, we got 9207 over 17,950. Now the question is it, maybe it's this possible P hat that yielded the table you actually saw. And if you're doing this, show its true base. So we're going to do the same process we did in part B, except with a little twist here. Instead of putting 0.5, we're going to assume that maybe it's not 0.5, but maybe it's 0.513 and see if we get a frequency table where the observed and expected counts are coming closer to each other, basically. Right? Because in this way, if you're looking at, for instance, let's say 4 heads versus one heads, it shouldn't have the same frequency. They should be slightly different. And similarly with all tails and all heads, it would not have the same possible outcome. Why is that? Because when you have 0.15 odds of having heads, it's slightly in favor of heads. So the frequency for 5 heads should be higher than the frequency of, for instance, 0 heads. The frequency for, let's say, 4 heads should be slightly higher than that of, let's say, 1 heads, which is what you're seeing here in the table. You see that, notice the frequency is slightly lopsided for more heads because it's slightly imbalanced in our likelihood of 0.15. So if you see the expected counts shows the same trend of the bias towards more heads because it's slightly biased in this direction, then maybe it's that possible coin toss, which is what we're looking at. Right? So now we repeat the process all over again. We want to construct the same table, but now we're going to change it because now our actual distribution using the same binomial, it's going to look like this. Instead of having 0.5 to the power of n, we have 0.5 to the x, 1 minus 0.5 to the n minus x. So it's not the same distribution. Sorry, it's not the same likelihood function because the p is changed in this context here. So let's see how we can go about this. So the expected counts kind of remains the same, right? So sorry, the observed counts is the same, but now we want to see how the expected counts change under this new, likelihood function. Okay, so we have to compute things again, obviously, right? And I started doing that. So obviously to save time, I said, okay, so P naught is going to be equal to 5 choose 0. But now, maybe I can make this a bit better because this looks kind of terrible, right? Now instead of having instead of having 1/2 to the power of 5, right? You have, well, if you have 0 possible heads, you get 1 minus 0.13 to the 5, right? So this should have a lower frequency than, let's say, this, because you see that when you put 0.5 to the power of 5, this is higher than putting 1 minus 0.15 to the power of 5, right? This is 1. This is 1, but this is actually bigger than this, right? So now we have all these P's, and I put ... dots, you can kind of fill it in yourself. So for instance, P, when you have 1 head, you're in this scenario here. Oops, This is one head, right? But so this is one head, for instance. Like my stylus is giving me issues. So this is one head here, right? But I noticed that again, it's changing. So you have 0.13 to the power of 1. 1 minus 0.13 to 5 minus 1, right? So you're going to keep doing this until you get the last one, which is 5 choose 3. Sorry, not 5 choose 3. 5 choose 5, basically, right? So I should put this here, should make this change. It's 5 choose 5, right? And you're going to compute them all, basically. So then after you do this, you multiply each of these possible probabilities by the expected, sorry, by the observations, basically, which is 3, 5, 9, 0. This is number of possible, this is number of trials, right? So let's make a note here. This is number of trials. This will give you the expected count, right? So I've done this, I've multiplied, so in my table, which I'm going to show you in a second, I multiply each of these probabilities over here on the left by 3,590. This is going to give me, right, the expected frequency. So if we go back and fill this in, you should get the following table. So this should be 90.5, but this one over here should be 127.5. So notice that it's higher, which makes sense because it's a slightly lopsided outcome. So I'm going to make this a bit cleaner. So this should be 51.3. So it's slightly lopsided towards heads, right? And similarly, this should be 518.3. And this should be 601.1. So you can see 0.5. So 605.1. You can see that it's actually changing in the direction of what you kind of see in your data. So you can see it's lopsided because you have a slightly imbalanced coin toss. This one here should be 191, so 1091.5. And this should be 1149.5. So notice that these expected and observed counts look a bit more proportional with each other. You can see the lopsidedness you saw in the previous one is dissipating, right? This is because we probably have a lopsided or slightly imbalanced coin toss where it's slightly more favored towards heads, right? So even though 0.49 and 0.51 seem similar, actually it's not. If you go to a casino, you have a 0.49 odds of, like, let's say winning, you're going to lose almost surely, right? But if you have a 51% chance of winning, you're going to win almost surely. You can actually show this is true in like, let's say, Markov theory, right? There's something called like, and you can show this in Martingale convergence theorem, right? You can use Martingale theory to show that this is actually consistently true. So this is kind of why it's called gambler's ruin, basically, right? This is the Martingale theory. It's called gambler's ruin. There's a reason why you don't actually necessarily want to gamble because it's slightly higher. You're slightly favored to lose. I think the odds of winning is like 0.49 something, which is a losing. Basically, you're not even guaranteed to break even, which is what the even is 1/2, which is so like you're guaranteed to lose almost surely, with odds that are slightly less than half. So this is kind of a disclaimer: do not gamble with that kind of favorable or unfavorable odds, basically. But yeah, so let's see how this changes things slightly, because now you might think to yourself, isn't the degrees of freedom the same? Can't we actually just do k minus 1? But not really, because you lost 1 degree of freedom when you estimated p hat, basically. So unlike the other one, which had degrees of freedom 5, you actually have degrees of freedom 6 minus 1 minus 1, which is the degrees of freedom you lost to estimate p hat. So you actually have 4 degrees of freedom, basically, right? So when you compare your test statistic, which ends up being 8.774, so take your count you see here, and do the same thing as we did in this section here, where I kind of walk you through how to compute this. And you kind of, when you look at the chi squared, I think it's an R. So this is actually, oh, did I spell that incorrectly? Let me see. It's chi, so it's, yeah, that's certainly not right. So chi square, but now you have 4 degrees of freedom. But anyways, it ends up being something like 12.83, which is certainly bigger than your computed thing, which is 8.74. So you cannot, this is a fail to reject the null hypothesis. You might say, what the heck is HO? Well, in this instance here, HO is actually the following. It's the P is equal to 0.513 versus the alternative, right? So you think that your actual P is something closer to what you hypothesized in your what you saw in your actual data, right? So you don't have evidence to conclude that this is not true. So you probably have a coin toss that is slightly biased, which is what we saw in part A. Okay, so now I'm going to switch to genetics, because question 44 is actually asking you to use the equilibrium formula. So where you have like, you have allele types, and it's telling you to go through the likelihood ratio test to determine whether or not your hypothesized P is consistent with what you saw in the data. So it's kind of similar, because it turns out we're going to use the same idea of a chi-square test statistic, but we're going to construct it a little bit differently. We're not going to use Pearson's chi-square. We're going to use a likelihood ratio test, and then we're going to compare it to a chi-squared, because it turns out that the likelihood ratio is distributed chi, and we're going to see how we can actually construct the test statistic ourselves and compare it to a chi-squared critical value. So I'm going to pause here and move on to that question. So the last question was actually, ironically, a biology question, which I haven't done in ages, but you are actually, well, the question actually comes from Rice 44, but it says derive and carry out the likelihood ratio test of the hypothesis, where you assume that theta is equal to 1/2. Now, theta is equal to 1/2, that has implications on the probability of seeing the allele type AA versus A little a versus 2 little a's, right? So this is what we're looking at. And so obviously we're going to be carrying out the test where we ask ourselves, is it true, given the data you saw, that you truly actually have theta equal to 1/2? Because that will, have implications into what your actual hypothesized proportion should be for each of the different allele types. So it's actually haptoglobin type, right? So this is what you're looking at here. So what you actually saw, so what Plato and et al. Saw was essentially that when you looked at the actual haptoglobin type, you saw that H11 or HP11 had a frequency of 10, HP12 had a frequency of 68, and then HP22 had a frequency of 112. So the question is then to determine the likelihood, like what's the odds of seeing that particular frequency if you truly actually have theta equal to 1/2. Now here's the little twist here, right? So you have to use these probabilities, because these represent the probabilities for, big AA, the heterogeneous allele type, and the homogeneous little AA. Now, we hypothesize that theta is equal to 1/2. So you can imagine that to achieve the, probabilities of, let's say, having a homozygous double large A, you have to actually plug in, 1/2. And then to find the heterozygous, you put in 1/2. And to find the homozygous little a, you put it in here. And that should yield your hypothesized theta. Now the question is, how different is it from the actual theta you saw? The estimated theta you saw is based on a sample of 190. So you can imagine that if I want to find, for instance, HP11, I would take 10 divided by 190. Then, HP12 would take 68 divided by 90. And then HP22 would take, for instance, like, 1112 divided by 190. And that, and work in that way, basically. Okay, so what I did was first of all, I kind of plugged in. So if it's true that the null hypothesis is, theta 1/2 versus theta not 1/2, well then, first of all, I know that this is multinomial because I actually have 3 theta. So you have a multinomial whenever you have more than 2 possible outcomes. In this case, I have 3. So what I'm looking at, right, is n choose. Well, now you have 3 possible realizations for each of the different, allele type combinations. And then multinomial distribution looks like, well, you take the probability of, that type and you put it to the power of like number of times that outcome is realized, and you keep going in that sequential way until you consider all the possible outcomes, right? Okay, so this is the actual likelihood under the hypothesis, right? So under the hypothesis of 1/2, I can derive PAA, where you have the homozygous big A, and then heterozygous A, big A little a, and then homozygous little a. So I've constructed it basically. So I know under HO that, the probability of seeing 2 big A's for allele type as well, 1 minus 1/2 the power of 2, which is 0.25. And then I could do the same game, right, for the heterozygous one, except now it's 2 times 1/2 times 1 minus 1/2, which is what you're given the question. And then the same thing is that you have 1/2 the power of 2, right, for little AA. Now, that's what you're hypothesizing. What you truly actually observed was what you saw here. So you have the estimate is actually 10 divided by 190 for, the big AA, right? So heterozygous PAA is going to be equal to 16 or 68 divided by 190. And this is coming, by the way, from the table, right? So I'm not pulling this out of nowhere. It's coming from these tables. And the last one is that you can almost see something's a bit suspicious, right? Because when you look at the actual last outcome, it's quite high, right? So 112 out of the 190 outcomes is little AA. That in our minds, think to ourselves, if this is really fair, how is the number of outcomes for little AA that much bigger than, by magnitude of more than 10, not of, big AA? So I'm going to use these probabilities that I've hypothesized here and the ratio of what I actually thought what I saw in the data. So this means that your actual ratio, which I kind of denoted this kappa thing here, is the ratio of the two things, the ratio of what I hypothesized and what I actually truly observed. Right? Okay. Now, if you actually, because of the fact that, of course, the number of possible outcomes for the, hypothesis, for the actual estimated P allele types, the proportions of estimated allele types, which is in the denominator, have the same power as in like the same number of trials. When you actually take the ratio of those two things, you're actually taking the ratio of because the multinomial distribution looks the same, except the proportion you put in is changing, you get PAA divided by PAA hat to the power of NA, because that's the number of times you saw the big A happen twice. And then you do the same thing the other two things. Now this is how we prime it in order to construct, in some sense, right, our likelihood ratio test. Now you guys know that it is not this thing here, the distributed chi. It's actually -2 log of that thing. So if I take the log, it means I'm taking the log of this entire thing. So when you take the log of this entire thing, you know that you have this rule in math. So I'm going to put in the corner here. So whenever you have log of AB, it's actually going to be equal to log of A plus log of B, right? So you have this 3 times, which is why you see you see these outcomes realize itself like this, right? So I'm literally taking the log of this entire thing, but with a little twist. I have to multiply each of these things times 2, which is why you see 2 times this. And then one of the, so not only that, you have the following rule here. So it seems very silly and pedantic, but these little things sometimes elude us when we're trying to do, we also have this rule here, right? So it seems really silly, but these little things escape us when we're rushing. So just to note that now this power of n, right, is being dragged down as a product, as a multiplicative factor, basically. So this is why you see, instead of having a log of this ratio to the power of NA, I can then I can put the n as a multiplicative factor. So it's me really simplifying this likelihood ratio, right? And the last thing is that you can see that there's a negative sign here. So notice I had to take the reciprocal of the thing you see inside the log, right? So instead of actually having a log of PAA divided by PAA hat, I flipped it basically. And then that undoes the negative, right? So it is a case that I could have put -2 in front, but then I'd have to have PAA divided by PAA hat, right? So the reason why there's no negative here is because inside the actual log, I've inverted the ratio basically, right? As you can see, if you compare this to this, it's inverted. If I didn't actually invert this thing, I had to put a negative in front of all the, so it would be negative 2 times NAA minus, 2 times N. And this should actually be, I missed it should be NAA. So it would actually be minus 2 NAA, and minus 2 and little aa. So I have to be a bit careful here, right? And make sure that I'm, being mindful of the sign changes. Now I'm going to admit that I did this in R just because it's so silly to do this by calculator when I can use this powerful tool that I really love, which is R, right? So you can see here that each of the components, now you know that the frequencies are given to you in the question, right? So this means that NAA is actually 10, right? And of the heterozygous A is 68 and the homozygous little a is 112. So I put this here. So it's 2 times log of like this ratio. Notice that what you actually expected to see, which is 0.25, what you actually observe is 0.026. This is going to be negative. When the ratio of what you expected to see, right, divided by what you actually, so this is what this is what you actually saw. What you expected to see is in the denominator. Whenever this ratio is actually less than 1, right, you will see a negative log. So this is going to be negative contribution to the actual test statistic. Similarly, you should have seen a half under the hypothesis that theta is equal to 1/2. So you should have seen, what you expected to see was half in the denominator, but what you truly actually realized, right, was something less than that. So this is a negative contribution again. Where the actual positive contribution happens is this huge ratio here, right, where you saw this really massive multiplicative factor. So this is in fact, more than 2 times what you expected to see, right? So this is almost 0.6, so it's more than 2 times what you expected to see. So when you look at this contribution, it's going to be positive, right? So if I just show you guys AA, it's in fact negative. If I show you AA, it's also negative, but if I show you little aa, it's positive. This is me actually labeling the actual parts of the log likelihood by the actual allele type I'm looking at. So if I add these things up, what I'm going to get is this huge thing coming from this, right? So we got a huge, massive test statistic, is what you see here, right? So I'm adding this up here. This is me doing it in R. It's my calculator, right? So now this is distributed chi. You know this is distributed chi, right? So just to put it out there, this whole thing is distributed chi. So this is distributed chi squared. And in fact, the degrees of freedom we have here should be 2 because, well, there are 3 different groups. So there's, if you take k minus 1, you get 2. So we're looking at a thing, right, that has degrees of freedom 2. And you can see that this is a 2-sided test. How come? Because the initial question said 1/2 versus theta, not 1/2. So this is a 2-sided implicitly. Right, and look at this massive test statistic. Imagine, right? So if I put this into R, or so if I literally just say, Q chi squared, right, at 0.975 and degrees of freedom 2, I get this thing here. But actually, your actual test statistic is so big. If I were to actually draw this out, it's something like really far out here, well past the critical value, at like 115.50, because it's astronomical, right? It's such a huge disparity between what you should have seen and what you actually saw that you're going to reject HO, right? So it doesn't seem as if this was even plausible. And so to address the question, did we actually see in nature what we truly should have seen if theta is equal to 1/2? Not truly, which is kind of funny, right? Because in some allele types, it's not true that the theta it's not true that it's 50/50 in terms of the contribution the parents pass to the offspring. In some instances, if my understanding of biological sciences, in some instances, it is truly the case that it's half. Like for instance, chromosomes, right? When it is truly balanced, like a father will pass X and Y with equal probability of 1/2, because the mother always passes X with probability 1. But it's not true for all allele types. So this is an instance where it's truly not the case that big A and little a have the same frequency. It appears that little a is actually more common, right? That's why you see it in nature much more amplified than what you see with double AA. And in fact, even the heterozygous allele type is more common than the two double A's, because in nature, this is, double AA seems pretty rare. So even the heterozygous, where you pass at least one little a, is more common than seeing this here, where you just have two big A's, right? So the intersection right there, which is pretty neat, between biology and statistics. If any of you are curious, it's called like statistical genetics, right? So this continues on, and there are a lot of people in the department, like Lei Sun, who are keen on statistical genetics. So if you're kind of curious, there's actually a continuation of, there's a graduate course in the stats department. I think it's STA261, but it might be cross-listed. So if any of you continue on and you're really curious to how probability theory intersects with like genetics, you can kind of either email her or continue to take the course, right? Continue on this 2-6 stream and eventually intersect these two areas of like sciences. But that is enough for me. Hopefully this tutorial helps you. If you have any questions, certainly I'll check the discussion board, and yeah, I'll post this on YouTube now. Thanks for listening. Have a great evening now at this point. Bye.